Okay, thanks for the introduction, and also I'd like to thank for this great invitation. So today we'll talk about the central issue in our community, material physics community, which is about the topology and superconductivity. And let me try to explain why I'm talking about these topics in this Quantum Korea conference. So in the community, in our community, there has been known for years the particular type of materials can be very, very useful for a so-called fault-tolerant quantum computation. So it is because, I cannot go into the details of this issue, but let me just put it this way. So there is a certain type of very, very special type of materials whose we call excitation. Let me just say this is a material property. There is a very special type of material whose material properties is very special. We call this as its excitation is following a non-abelian statistics. It can be very useful for fault-tolerant quantum computation. It is because this material is very robust against the external perturbation. Let me just put it that way. And then, yes, this is it has been known for many, many years, at least for 30 years. And then our interest come to the next question, which is about what are such materials? Where can we find those materials, or how can we make them? Okay, so there has been some material candidates. Probably the early stage, lots of discussion paid to we call the fractional quantum Hall materials, and also it's relatively recently, around this 2008. There has been a very interesting suggestion, which is about S-wave superconductor. S-wave superconductor is, most of superconductor are actually the S-wave. So the very conventional superconductor, if we can put it on another very special type of material we call the topological insulator, then this interface can be such a material. Okay, so this is an quite interesting idea, and there are some other possible candidates, such as frustrated quantum magnets. I don't want to go to the details into direction, but anyway, there has been many suggestions, and we are still searching for those materials for quantum computation. And today, my focus is on about this topological superconductor. Topological superconductors are also another possible and very promising platform for realizing such an anionic or non-abelian quasi-particle platforms. So what are those materials? Well, this is very rare compared to the previous cases. First possible candidate is so-called P-wave. The previous superconductors was, I said, is S-wave, but if we can find P-wave superconductor, we are pretty much likely in making such a possibility, okay? And another possibility that I want to focus on today is about S-wave superconductor with its surface topology is very special. The surface topology is the topological insulating, okay? Then it's okay. Then it's also, we will be very happy, okay? So, in fact, there has been relatively recent examples that reports they found, actually this is the final case of S-wave superconductor with surface topology. And the material is something like this. And I can show you the published data from ARPIS, and also we call STS data. At the zero energy, you can probably see some small tiny peaks. That is very important, actually, because the authors interpreted them as a possible indication of the Majorana, we call the Majorana excitations. Of course, we need to and on one hand, we have to confirm it, and if it is real, we have to probably consider how can make use of them. But on the other hand, I think we have to keep searching other promising material platforms, okay? If we are really serious about the applications, okay? So here, as a theorist, as a theoretical physicist, I'd like to suggest a so-called first principle-based computation search of new materials, okay? And in this idea, we call the density functional theory, or simply DFT, plays a central role. DFT is very nice in the sense that it only requires us to give minimal information of a given material. Namely, DFT simulation only need an input, only two types of input. One is a chemical composition, and another is atomic structure, which is the minimal set of defining a given material, okay? And by having that, it can give us such many information like total energy and electronic band structure, and also many different types of response functions, okay? So that's the powerfulness of DFT, or first principles simulation. And indeed, there are many successful storylines. People have been finding out successfully the new quantum material based on the first principle simulations. One important success story is actually about the topological materials. There are lots of materials. So I cannot put some representative examples here, but I just put one very first topological insulator, which was found in the mercury telluride quantum well structure, which was actually guided by theorist. This is actually the paper. And after that, there are so many examples. Okay, so as far as, if you can tell me any specific type of topological material, I can probably tell you how, if you examine the history, almost certainly it was guided by first principles computation, and then experiment followed up by those. So around 2020, there are a series of Nature papers which you can, from their titles, you can recognize the word catalog. So this kind of theoretical design or search became so powerful that theorists tried to make a catalog. Okay, so tons of material they searched and they made the catalog. Of course, it will be very useful for experimentalists to search for a new quantum, especially the topological material. And finally, this kind of effort has been appreciated by American Physical Society. You can see the prediction, which is coming from pure, highly theoretical physics, and experimental realization. And between these two, there was a design of real material, which has been the work of first principle simulations. How about the superconductivity? Well, superconductivity has a longer history in physics, almost more than, actually longer than the 100 years. So this is a little bit complicated. As far as the conventional superconductivity, these are the y-axis. You can see the superconducting critical temperature, and there are so many different types of materials. And the same color refers to the same type of superconductors. And the highest TC materials can be found in here. They are green colored. I hope you can see these green colors. And they are actually conventional, we call the BCS type superconductors. As far as these materials are concerned, we are, I would like to say, very good at designing and searching for new materials, okay? So as my friend Warren Pickett wrote in his review paper published quite recently, he mentioned that by 2000, given a known compound, the superconducting TC and superconducting gap function and several other properties of superconducting state become available independent of further experimental input. So without any experimental input, we can examine all those superconducting properties. And density functional theory-based computational material design has progressed to a predictive level. So this is the current state of the art, okay? However, unfortunately, this is not the end of story, okay? So there are so many other types of superconductors known for many years also, at least 40 years or 50. For them, we are pretty much limited. The one demonstrating example is about the most recent case of nickelite superconductivity. For that, I can tell you a long story of failure of our theory, okay? So many great people have tried to predict a nickel-based superconductor, which is believed to be unconventional. However, we want to try, design, or find out new materials. And many great people try to do that. But this discovery, 2019, actually provide us another example of our failure, okay? So it is much more challenging, but I don't want to say that we cannot do anything, but we can do great jobs, but compared to the conventional superconductivity, our predictive power is pretty much limited, okay? All right, with this background, I'd like to report our recent progress, okay? So this is my material, so based on the first principle simulation technique, we tried to find a new material that can be useful for quantum computation. I mean, superconducting material with a special type of band topology. So here's an example. This material is actually quite well known. I know some audience, or my audience, there are some experts. This looks like this, okay? And this is a magnetic material. This is a structure of my material, and this is a spin structure of my material. I don't want to go to too much details here. But this is known to be non-superconducting, okay? But by applying pressure, it becomes a different material, okay? Its structure changes, its magnetic structure also changes, and finally, it becomes superconducting under such high pressure. Like this is not very high pressure, okay? So like a 10 GPa or 15 GPa, these two materials at least become known to become superconducting. The TC is about, let's say, 10 Kelvin, which is not very high but not very low. So with these experimental reports, in this case, of course, experimental reports came first, and we got interested in this material, and we performed this kind of computation. This is a kind of standard computation scheme. So first thing we want to do is to examine the so-called phonon band dispersion and phonon density states. So phonon is a lattice vibration or atomic movement, coherent atomic movement in a given material. And the red colored line we call as phonon bands. And the blue colored line we call phonon density states. And this A square F or alpha square F we call Eliasberg function, which is the key information it contains for regarding the BCS type of superconductivity. So by looking at this function, we can very nicely guess whether the material is superconducting or not, okay? So for me, okay, these two materials are very, very promising to become a superconductor, okay? I don't, even if I cannot tell you the details here. So based on this information, we finally estimate superconducting TC. So this y-axis is superconducting TC. And yes, there are 4 different materials, okay? And let me first look at this point. So this point is about iron P sulfur 3. And my theory, my calculation tells me that this superconducting TC is 0, which means it is very unlikely to become a superconductor, okay? And it is consistent with experimental observation because experimentalists could not find superconductivity for this material. However, if I replace this iron by nickel, it becomes superconducting. You can see my theory, my calculation tells me depending on the pressure, but it clearly shows me the finite superconducting temperature, and this temperature is actually in quite good agreement with experimental reports. Okay, so by having this information, we can presumably conclude that this material is likely a conventional BCS type superconductor. And finally, I'd like to focus on this red line. Okay, this is the case for iron and selenium. For this, my computation tells me is superconducting TC is not 0, but is very close to 0. Okay, so in this case, it's a kind of difficult situation, but we are fortunate to have an experimental reports which tells us the order of magnitude higher superconducting temperature. So we temporarily interpret this information that this material can be, I mean, maybe unconventional superconductors, and we are pushing toward that direction. Okay, let me skip that one final point over here. Okay. All right. Finally, we want to also check up the topology of this material. This is a really too much detail. So, but I like to tell you that the topological property of a given material is a kind of very well established technique we have. Okay, so it's a very standard one. Okay, so this is a band structure of this material. I mean, this material, and this is so-called topological index. We call the Z2 index. And by having these numbers, we can conclude, we can know what kind of topology it has. So this is 1, 0, 0, 0, 1 something you can see. And as far as this first index is 1, not 0, then we know that this is a topological insulator. Okay, so all of these four materials under pressure is topological insulator, Z2, and strong topological insulator. And some of them, and two of them, is actually superconducting, so it can be promising platform for further applications. So let me conclude my talk with having these two statements, and I'd like to thank for your attention.